In this video, I'm going to cover a limitation of the recursive descent algorithm that I presented last time. Here's the grammar from our last presentation, and here's its implementation again as a set of mutually recursive functions that together implement a simple recursive descent strategy. And now let's think about what happens when we go to parse the input int, the simplest possible input string. Well, let's work through it. So remember, we start with the function that implements all the productions for the non-terminal e. And so what we're going to do here is we're going to call e, and that will try calling e1. All right, and what is e1 going to do? E1 is going to call t, because of course the first production is e goes to t. So let's take a look at what t does. T is going to try out the production t1. All right, and what does t1 do? Well, t1 recognizes an int, okay, so that's good, and it will match it and return, okay, and then e will return and we will succeed in parsing. And I forgot to mention that also in the process the input pointer will be moved across the int, and so when we're done, e will return and we will have succeeded in parsing the string int because e returned true, the production for e returned true, and we consumed all of the input. All right, so now let's consider a slightly more complicated example. Okay, so let's try the input string int times int. All right, so again, we start with the production e. Okay, and the first thing we'll do is we'll try the production e1. Same thing we did last time. E1 is going to call the function t, and t is going to try the first production for t, which again is the production int. Okay, and the input pointer, of course, is here, and then it will try to match that against an int. Okay, try to match the first token in the input stream against the terminal int, and it will succeed. Okay, and so the input pointer will be moved over, so t1 will return true. All right, and as a result, this right-hand side here of the function t will also succeed because t1 returns true, so t will return true. Okay, therefore e1 will return true, and e1 returning true will cause e to return true, and in fact that will be the end of the execution of the program. We'll terminate, e will return true, and the input pointer will only have advanced as far as int, and so we will reject the parse. This is actually ends up getting rejected. And the question, of course, is what happened? All right. Why didn't we succeed in parsing this input, which is clearly in the language of this grammar? Well, the story here is actually a little bit interesting. What happened is down here, when we discovered that int matched the first production for t, we said that t was done, okay, that t had succeeded and had matched its input. And then when e ultimately returns and the whole parse fails because we haven't consumed the input, we don't have a way to backtrack and try another alternative for t. If we were going to succeed, we would have to say, oh, well, even though we found a production for t that matched part of the input, since the overall parse failed, that must not have been the right production to choose for t. Maybe we should try some other productions for t. And in fact, if we had tried the second production for t, t2, we would have matched int times t, and then we probably would have succeeded. We would have been able to match int times int. Okay? And so the problem here is that even though there is backtracking within a production, while we're trying to find a production that works for a given non-terminal. So while there is backtracking for a non-terminal during the time that we're trying to find a production that works for that non-terminal, there is no backtracking once we have found a production that succeeds for a non-terminal. So once a non-terminal commits and returns and says, I have found a way to parse part of the input using one of my productions, there's no way in this particular structure, this particular algorithm, to go back and revisit that decision and try a different production. All right? So the problem is that if a production for non-terminal x succeeds, there's no way to backtrack to try a different production for x later. So once the function for x is returned, we're really committed to that production. Now that means that the particular recursive descent algorithm that I showed in the last video is not completely general. And recursive descent is a general technique. There are algorithms for recursive descent parsing that can parse any grammar. They can implement the full language of any grammar, and they have more sophisticated backtracking than what I showed in the algorithm that I presented last time. Now, the reason for showing this particular algorithm is that it's easy to implement by hand. So this is actually an algorithm or an approach to recursive descent that, while it has this limitation, as you can see, it's very mechanical and very straightforward to design a parser for a given grammar. And it will work for a rather large class of grammars. So in particular, it'll work for any grammar where for any non-terminal, at most one production can succeed. So if you know from the way that you've built your grammar that in any situation that grammar can get into, or the recursive descent algorithm can get into during parsing, that at most one production can succeed, then this parsing strategy will be sufficient, because there'll never be, once you find a production that succeeds, there will never be a need to go back and revisit that decision, because it must be the case that none of the other productions could have succeeded. And it turns out that the example grammar that we're working with in the last couple of videos could actually be written to work with this algorithm. All right? And we would have to left factor the grammar. Well, actually, there's more than one way to rewrite the grammar to work with this recursive descent algorithm, but one way to do it is to left factor it. And I'm not going to say any more about left factoring in this video, because that's going to be a topic of a video that's coming up shortly.